All right, good morning. We're going to get started at the GDC Technology Theater here at the NVIDIA booth. I wanted to present to you Ronaldo Zioma from Unity. He's going to be talking about Unity and Shadowgun. So take it away.
Okay. Hello. Hello. It works. Today I will talk a little bit about the Shadowgun optimizations we did for Tegra while working the Shadowgun. Some filler. And the Shadowgun is actually developed by Madfinger Games. And there was some collaboration with Unity, so we more or less helped them with the optimizations and some small features. And the previously Madfinger Games, they released Samurai and Samurai 2, and Shadowgun was their third project. And it took they started as a small team, grew it a little bit, and it took them around 7 months to finish the game. And if you haven't seen it yet, it's a third-person sci-fi shooter type of game, kind of. Yeah. And lots, when we started to thinking how would we do it, how it should look like, we were looking at the sci-fi kind of movies, and all of the visual look, style, and what eye candies we wanted to bring into the game was more or less coming from the movies. And that type of the gameplay involves large both indoor and outdoor environments. So it's pretty expensive kind of game for the mobile platform. So we had to spend quite some time trying to optimize it. And that's the final result. It runs 30 frames on it, both Tegra 2 and Tegra 3. And the difference between Tegra 2 and Tegra 3 has a more enhanced version, much more things going on. So they run both at the 30 frames per second, but actually there is much more stuff in the Tegra 3 version. And on both Tegra 2 and Tegra 3, Shadowgun is actually GPU bound. And the reason on Tegra 2 it's GPU bound because there's quite a lot of the pixels. And on the Tegra 3, just tablets tend to have quite high resolution screens for such hardware. And on Tegra 3, we crammed as much as possible into the picture, but it's not CPU bound just because the Tegra has very fast 4 cores. So the main time we spent on optimizing was actually optimizing the GPU time. And the first thing which I need to say that you need to use NVIDIA of Heart. It's a very good tool for profiling. Probably one of the best tools on the mobile platforms, and it gives you almost all the information you need to optimize the game. It's very easy to use, especially if you used it on a desktops before. So basically, what it gives you is a breakdown of the frame, and you see all the draw calls. Basically, it captures the current state of the game. It pauses the game and gives you all the draw calls which were sent to the GPU, and then it gives you timing, how much time every draw call took on the GPU side, and you see how much time it's more or less spent on inside the vertex processing and inside the pixel processing. So that is a great tool to get the picture. What is the most expensive part of your frame and how to optimize it. Okay, in order to get Shadowgun running at 30 frames per second, as I said, that's more or less the three key points which we had to do. And hand optimizing shaders, basically. And the most important thing there is to pick the right precisions. Usually need to use as low precision as possible for all your components. Sometimes that can give you a bad visual quality, so then you go a little bit up from that. So it's a little bit of experimentation there, but it's very important to get to understand how the precisions and how to use them, because using like full flow precision versus fixed precision can give you almost 4 times difference. Instead of doing we wanted to per pixel lighting on all our characters and weapons, but doing that properly with the proper calculations was a little bit too expensive. So instead we just developed old school kind of way of using lookup textures to sample the lighting. I will talk about that a little bit later. It was not feasible to use post-processing. Instead, we decided to get the overall look of the game, the base art, and the amount of geometry as high as possible and not spend it on the post-processing. And to get all those glows and volumetric effects, we opted to hand-placed alpha-blended geometry, which we could control at the runtime to minimize the overdraw. So instead of like post-processing, with the post-processing, you always work with the full frame. But if you place only some alpha-blended geometry here and there, then you don't need to spend on the glows. You don't need to spend the whole time. You don't need to cover the whole full frame, basically. You just need to place them where it has to be. So it saves you on the fill rate. The one thing, this is when submitting geometry to GPU, it is important to know that if you both read and write into the same VBO from CPU side and from GPU side, the GPU will be stalling. So we have like a pool of VBOs because we have quite a lot of dynamic geometry. So what we do is we allocate, pre-allocate a bunch of VBOs and we rotate them. Basically, we always know that when the CPU needs to write something to the VBO, it grabs a new one, writes data, and then next time it grabs next VBO from that pool, and the GPU is kind of coming from the back. So there is always a big how to say big gap. The CPU is always far ahead from the GPU when it comes to writing the dynamic geometry. And probably the most important thing for the Tegra is to sort opaque geometry. Tegra has the zcal functionality, which allows to reject pixels if they are already covered with some geometry, which was rendered before, and if you render pixels behind that, they can be quite trivially rejected. So to get, and it's much cheaper than actually the rasterizing that pixel. So in order to get full advantage of the zcal, you need to sort your geometry. You need to sort all the opaque geometry from front to back. And it's a little bit of the balance, because if you just sort the geometry from front to back, at the same time you get quite a lot of the shader changes and state changes. So we kind of try to balance here, and we sort them in so-called buckets. So we take like our geometry in first 10 meters, that's one bucket. So inside that bucket, we render that bucket first, and inside that bucket we would render the draw codes by the shaders and to minimize the render state changes. So we have like several buckets basically. All the distance in the camera space is divided in several buckets. So it's roughly sorted front to back geometry. We did some tricks basically because we always know that the character is in front of the camera. Most probably it's always covering quite a lot of view, so we force character to render first. And we know that the enemies are usually hiding, so we force enemies to render after the level was rendered, because they are usually behind some wall or crouching behind something. So we force them always to render after all the environment was rendered. And the skybox is usually occluded by everything else, so we force skybox to render it last. And just doing that, all these things I don't hear, that saved us 15 milliseconds on the GPU time. So it went from 20 frames to 30 frames just by sorting geometry. Okay, of course you want to use DXT5 on Tegra, and with Unity it's very simple. It's when you build your application, you just pick the target, and the target is Tegra here, yeah, and it will use DXT5 compression. We try to use Neon coprocessor as much as possible. They are very powerful on Tegra. You have 4 of them. So we spent some time optimizing, handwritten assembly for them, but it really pays off. And what we do is we do skinning, water simulation, cloth, a little bit of the cloth, and parts of the character animation are done as well on the multiplaying matrices, basically. That's all done in Neon. And it's parallelized, so it can take care of all 4 cores. So next I'll talk a little bit about how we structured our lighting. And it's pretty simple. For the environment, we picked to use light maps. And for dynamic geometry, we're using light probes. I'll talk. Light probes is some new functionality from Unity, which is available in 3.5. And light maps was always there. Like baking light maps is pretty trivial. I just want to show what resolution we picked for the light maps. So we picked a 1000 by 1000. It's more or less per level, and it's uncompressed. The reason to be uncompressed is that it gives smoother GI, much smoother lighting. If we compress the texture, then it takes less memory, but it doesn't look that good, even if you upscale the resolution. So we opted to use uncompressed textures for the light map. Light probes is, as I said, it's something which comes from the Unity 3.5. Basically, it's a bunch of points in space which capture the incoming lighting from all the sides and store it as a spherical harmonics. And it's really easy to figure out for your object which points are closest to him, and we can interpolate, and we can figure out basically the whole incoming lighting for the character in that way. And we store around 500 those points in the level. They are more or less hand placed. Well, it's pretty easy to do that. And they are spaced every 3.5 meters, more or less. And that allows us to perfectly match both dynamic geometry and static and the level environment. So if you have some lighting inside the level, we don't really need to put any additional lights to light dynamic objects. They just automatically catch the lighting coming from the light probes. We wanted some specular highlights on our static geometry. And usually, nowadays in the modern games, people use so-called directional light maps or radiosity normal mapping. That was not feasible to achieve on a mobile platform. So instead, we did this fake thing to get some sort of a normal map kind of look on a static environment and see some sort of a specular highlights on that geometry. So what we did is we create a virtual light which casts only specular. Like you can see the specular highlights all the place. That's coming from the single point light, which casts only specular light. And it's always kind of attached to the camera. It's like always hovering 1 meter above the camera. Not exactly from the eyes, but a little bit from the side. So it gives, as you see, it gives this highlighting for the level. And to get much, and we calculate that per vertex. But to get per pixelish effect, we use a special, just a mask texture. It's stored in the it's stored in the alpha channel. All textures in a level, and that alpha channel gives basically a factor how much spec highlight do I want at this point. So once we multiply it, it gives this per pixelish effect, and you see the lights, kind of the response, the specular response when you move through the level. Next thing, we wanted to achieve volumetric effects. And you can see here, there's like a halo here on the top. The sun is pouring through the shaft, and there is some sort of a halo, lighting halo. There are some halos around the the lights, and there is a light pouring from the side here, like a God rays, kind of. So all that, we wanted to achieve that, but we didn't want to do a more expensive post-processing for that. So instead we opted, and I can show how it looks, how the level looks without volumetric. So it's much more boring and flat and boring, and here it gives much more depth and interest. And it can guide you as well, like the gameplay-wise. So we decided to, instead of doing the post-processing, we decided to do it in a smarter way. So, as I mentioned before, we put, or Matt Finger artists put a lot of alpha blended geometry. It's a static geometry, usually rotating together with the camera, or sometimes even animated. It gives us better way to control the performance. As I said, we don't need to spend all the time on the full screen post-processing. You see it here, like the volumetric effect. So, and to optimize them, we went with the very simple fragment shaders. But the most interesting thing is that when you're coming closer to them, they usually tend to cover quite a lot of the screen, and then you tend to get quite a lot of overdraw, and such things can get very expensive. So the rendering guy on Madfinger team came up with this solution to that. So what he does, he shrinks the surfaces when you come closer to those effects. He starts shrinking them basically away from you. And the artist will put like a normals on the geometry, on all that volumetric geometry. They would put the normals, which will tell in what direction to pull it back. So if you have like a light shaft pouring from the side, the normals on that geometry will tell you that when you're coming closer, the geometry needs to shrink towards the light. And if it's some sort of a light bulb casting the lighting in both directions, then it will go like shrink this way. And that is a very good way to control amount of the overdraw. Basically, the closer you get to this volumetric geometry, the smaller it gets, covering less and less screen. And at the same time, you decrease transparency. So it's barely visually it's barely noticeable, but it gives really good performance, gives very good performance improvement. Another thing I wanted to show in that screenshot is the fog planes. So instead of doing the full fog, like you see it in the background, there's a greenish fog. So instead of doing fog per fragment, which is kind of expensive on a mobile platform, we went with this fog planes, which as well the artist would put them wherever they are needed in the distance. And as you're coming closer, they are fading out. So they never cover the full screen. They usually you see them covering maybe 30% of the screen. And if we would go with the calculating fog per pixel, we would have to do that for every pixel, and it would be more expensive as well. Even the fragment calculation itself would be more expensive, because with the fog planes, the shader there is extremely simple. You're just outputting single color basically. So it's very tweakable. Artists can put them whenever they want, and they can tweak the parameters really easily. So for characters, that's basically our budget for the Shadowgun budget for the characters. You see that the main texture is 2000. The normal maps are 1000 by 1000. They are uncompressed to get a better quality. And for the lighting, we use small lookup textures. You see the vertex budgets and amount of bones. Usually when it takes around 3 to 5 milliseconds to calculate all the skinning for those characters and animations. Oops. Okay. So, as I said, we wanted to have a per pixel lighting on the characters, and doing that in a traditional way is kind of expensive. And the most expensive part is in this formula that on the top there is a formula which is like a normal per pixel lighting. And the most expensive part there is this when you need to rise specular to the certain, like you do dot product between normal and the half vector, and then you rise it to the certain power, the spec power. And the spec power is quite expensive. So we're looking to way to optimize that. And the one of the ways, of course, to use texture lookups. Just to do this power, instead of doing the math, we could use power, pre-calculated powers using the texture lookups. But then we figured out why do that only for that part. We could store all the result in the texture. So we have those 2D textures for the character lighting, which I wrote a very simple editor directly in Unity, which allows you to generate those textures. And basically you have a very flexible lighting this way. You can have both like key light, backlight, fill light. You can have some wrapping, light can wrap around the corners a little bit. You can have some like much more complicated lighting equations. And all that doesn't cost you anything because it's just a single texture lookup. So artists can just go and tweak those parameters, and that's how they get lighting on the character. And at the runtime, we just do a single texture lookup. We calculate the dot product between normal and lighting, and between normal and the light direction, and between normal and half vector. And then we just use those numbers to look up into the texture. And you can see here that's how this texture looks like. And in the RGB channels of that texture, we store the response, the diffuse response. And in alpha channel, we store a spec response. So at runtime, we just need to combine them. Basically, it's just a couple of instructions. And all that shader, on top of that, we actually add the global illumination coming from the light probes. And we hack kind of the muzzle flash into the light probes as well. So all the dynamic lighting doesn't cost us anything either. So we combine this directional sign lighting with this pre-calculated texture lookup, with the lighting coming from the light probes. And we evaluate light probes per vertex, and that is done per pixel. And we combine them in a fragment shader. And the result of that is 10 cycles, I think, as far as I remember. So it's very, very small fragment shader, and you can get very good results with that. It's much more flexible than doing the proper lighting. Yeah, we wanted some soft shadows from the character, sorry. And it's basically always a plane, kind of, below the character. And there are 3 spheres attached to that character. And in the vertex shader is actually doing some sort of almost a ray tracing to find the distance and how much. I'll show you. Here you probably see there's like a plane below the character. And it's tessellated, pre-tessellated, like manually pre-tessellated. There's a bunch of vertices. And every vertex calculates basically how much it is occluded by the 3 spheres. And the spheres are attached like to every leg and attached to the torso as well. So you get this nice, soft shadow look behind the character. And that plane is always walking with the character and just blended on top of the environment. We only for Tegra 3, Madfinger has added interactive fluid surface. So I will not go into the details. There's quite a lot of papers how to do actual physics simulation, but basically it's just a simulation of height field simulated on neon coprocessor. So it's a wavy thing, and then you can shoot in that, and it's all kind of simulated on the CPU. And you can see the number. We usually use 128 by 128 fluid grid. I have some times here, and the C++ implementation originally took 1 millisecond, almost 1 millisecond, and then rewriting it more or less in naive neon code in assembly made it twice as fast. And once we calculate that grid, we reconstruct mesh from that, calculate position as enormous, and just render it as a terrain kind of, as a mesh. And it's pretty simple. Uses pretty simple shading, just blending between the shallow and deep water colors, depending on the height and on the angle. And for reflection, simple cube map is used, which is just taken from the center of the level, more or less. The Fresnel effect is calculated per vertex, and in practice, the water could look much better if there would be more GPU time to spend on that. It's a pretty simple way to do it. And I think that's it for today. We are having a conference this year at Amsterdam, so you are welcome if you want to know more about the Unity. Do you have questions, guys?